As we continue working on more contradiction proofs, be careful and please write down as many details as you can in order to avoid confusion. We don't want to confuse you or the reader of your proof. So anything you think is helpful, go ahead and write it down. It's better to have a little bit more information than to have less information. And remember, proofs by contradiction and later on proofs by contrapositive will require some sort of negation right off the bat. So in this case, theorem 4.6.1 basically says there is no greatest integer, and we showed how that could be true by supposing the opposite of it, saying that there is a greatest integer, and showing that that statement leads to a contradiction, which makes this statement false. Let's take a look at another problem, 4.6.2. This is a theorem in your book, and it says there is no integer that is both even and odd. And if you didn't know, this statement is obviously true as well. So let's go ahead and take a look at how we can prove this statement is true by doing another proof by contradiction. So to begin, again, I'm going to write the words proof by contradiction at the very start. This is again to remind folks that I'm doing a proof by contradiction so they can expect to see on the first line of my proof the negation of the theorem itself. Okay, so I'm going to begin with the words suppose not. And what do I mean by suppose not? I mean that we want to suppose, for the sake of contradiction, those words just mean that we want to suppose so that a contradiction will happen eventually. We want to suppose that there is an integer that is both even and odd. Now this is some sort of crazy nonsense. We already know this because we've had some experience dealing with mathematical concepts. But in case somebody is seeing this for the first time ever, how can you convince them that this is some kind of crazy statement? Well, we want to lead the person to a contradiction, basically. So what we're going to do is this. Since we're assuming that there's an integer that is both even and odd, let's go ahead and call that integer by the name n. So n is supposed to be the integer that is both even and odd. Now again, we know that this is crazy, this cannot happen, but we're assuming that there is such a number. Since n is even, then by the definition of even, n can be written as 2 times k, where k is some sort of integer. We know this by the definition of the word even. But n is also odd, so then because it's odd, the n number can be written again as 2n plus 1 by the definition of the word odd. Okay, but wait a second. The first n and the second n are the same number, so that means that we can set them up to be equal to one another. And by direct substitution, we can replace the 2k first and the 2t plus 1 next. And subtracting 2t from both sides, we get 2 times k minus t equal to 1. This is just simply by factoring the 2's. Now keep in mind that k was an integer and t was an integer, so k minus t, the difference, is still going to be an integer. This is known as the closure of integers under addition or subtraction or multiplication. In other terms, if you multiply or add or subtract two integers, your solution, your answer, will still be an integer. Now, why is that useful? This is useful because this is saying that 2 is going to divide 1. Remember, we said 2 times k minus t is equal to 1, and k minus t was an integer. So that means that 2 divides 1, which is a contradiction with the previous theorem. The theorem was 4.3.2, and it says that the only divisors of 1 are 1 and negative 1. So how could 2 divide 1 when the only divisors of 1 are 1 and negative 1? Now, in the previous section, in section 4.3, I did not prove this. I just told you that the proof is in the book, but we didn't actually prove it. So I would advise you to look at the proof if you haven't. But the proof basically shows that the only divisors of 1 are 1 and negative 1. 2 is not in there, which means that our assumption that there is an integer that is both even and odd must be false. It's leading to a contradiction, which means that the statement of the theorem must be true.